Hello, welcome to today's session of chemistry. In today's session, we're going to talk about two of the very important compounds in organic chemistry, and they are alcohols and phenols. So let's get started. Okay, so this is how the structure of alcohols and phenol looks. In alcohol, the hydroxy group, the OH group, is connected to the alkyl group. R here represents alkyl. The alkyl group could be methyl, ethyl, propyl, and so on. In case of phenol, the hydroxy group is attached to the benzene ring. Okay, that's the structural difference. So having said that, one thing we should be careful is when I say the OH is attached to the R group, the alkyl group, we also need to know that the OH is attached to a carbon that is sp3 hybridized. Okay, so in alcohol, hydroxy group is attached to a carbon which is sp3 hybridized, usually a single bonded carbon, right? In case of phenol, the hydroxy group is attached to a sp2 hybridized carbon. This carbon center right here is sp2 hybridized. If you look at the number of electron domains, or the steric number for this carbon is 3. There's one bond right here. This is 2. And that is 3. Whenever the number of electron domains around a center is 3, that's the sp2 hybridized center. Whereas in this case, the carbon connected to the oxygen, the carbon right here, would be sp3. That's a very important distinction right in the first place. Okay, there's one little exception to alcohol. There are also alcohol in which the hydroxy group is connected to sp2 hybridized carbon, a double bonded carbon. Those are called alkenols, but these are not really important, okay? They undergo isomerization and get converted to a carbonyl form, aldehyde or a ketone, which are more stable. So we don't really need to worry about the alkenols for this session and for this study of alcohols in general, okay? But just research into alkenols and see what you think about them. For now, we'll remember in alcohols, in 99.99% of the alcohol, hydroxy group is connected to a carbon that is sp3 hybridized. In phenol, hydroxy group is connected to the carbon that is sp2 hybridized. Okay, so now that the connection to a sp2 hybridized carbon versus sp3 hybridized carbon is going to have implication, which we are going to study later on. But the first difference, okay, let's say this is the second difference, right? The second difference is basically in terms of acidity. I've given the pKa value for ethanol here, and the pKa value for other alcohol would be very similar, 16 or more than 16, okay? For phenol, the pKa value would be around 10 or even less than 10 for phenol derivatives. What does that mean? What does higher pKa versus a lower pKa value mean? Whenever your pKa value is higher, that means the acid dissociation constant, Ka, the value of the acid dissociation constant is lower. That means the substance is less acidic. Okay? If the pKa value is lower, that means the corresponding Ka value is higher. Higher Ka value means the compound would dissociate more in solution, producing more H+. That means it's going to be highly acidic. Okay? So lower the pKa value, more acidic the substance. So between alcohols and phenols, the phenol are more acidic. Very important property. We'll see why. So what I'm doing here is I basically ionized a phenol in a solution, in aqueous solution, right? Giving a phenoxide ion and hydronium ion. And also I've done the ionization for the alcohol. So alcohol plus water in solution, it's going to give you alkoxide and hydronium ion. So the way we're going to compare the acidic nature or acidic trend of phenol and alcohol is by seeing which one undergoes this ionization process more easily. For which of those two compounds is the ionization process more efficient? Okay, and in order for the ionization process to be more efficient, we have to check the stability of the corresponding conjugate base. Okay, phenoxide is going to ionize into phenol, is going to ionize into phenoxide, which is the conjugate base. Alcohols are going to ionize into alkoxide. This is the conjugate base. Now comparing the stability of phenoxide with alkoxide, we can compare the acidity of phenol and alcohol. If phenoxide is more stable than alkoxide, this reaction is more likely to happen, or this happens more than this, making phenol more acidic. If alkoxide is more stable than phenoxide, this reaction will happen more than this. The dissociation of alcohol is more than the dissociation of phenol. That means alcohols are more acidic. Now let's compare the acidity of phenoxide with alkoxide. So if you look at phenoxide right here, what you can see is this lone pair of electron can come here, make a double bond, and this double bond can go here and create a negative charge. And again, further, this negative charge can move here, and this double bond can make a negative charge here. Again, this negative charge can make a double bond here, and this pi electrons can localize the charge here. What that means is this negative charge on the oxygen can be delocalized throughout the ring. Very important distinction, okay, very important factor. The negative charge on the oxygen is easily delocalized through the ring because of the presence of this alternate single and double bonds. Whereas in case of alkoxide, there is no way this negative charge would be delocalized, which means higher the delocalization, more is the spreading of charge, more the dilution of charge, more is the dispersion of charge, more stable the product. Less the dispersion of charge, less the dilution of charge, less the delocalization of charge, less stable is the product, or less stable is that compound or the ion, right? So phenoxide would be more stable than alkoxide. That means the ionization of phenol is much more in comparison to ionization of alcohol. As a result, phenol is significantly more acidic than alcohol. We also saw that theoretically in terms of the PKA value, right? The PKA value was good enough to tell us that phenol is more acidic, but we now know why phenol is more acidic than alcohol. It's because of the higher stability of phenoxide ion in comparison to alkoxide ion. And why is the phenoxide ion more stable? I've shown the picture here. You can look at it. The negative charge on the oxygen is delocalized throughout the ring. It can sort of move throughout this ring. As a result, there is no concentration of charge. Not having charge concentrated at one center is a good thing. That will make the structure more stable. So learn how to do this arrow pushing diagram for phenoxide ion, which is not possible for alkoxide ion. Okay, so number one, besides the basic structure, phenols are more acidic than alcohols because of this delocalization of charge. Okay, so this figure I found was pretty interesting, so I just put it here. So what it shows is basically the PKA comparison between phenol and alcohols. So up here, all these are basically alcohols, and down here, these are phenols or phenolic derivatives, phenol derivatives, okay? So the phenol that we talked about earlier, the OH connected to the benzene is right here, and the pKa value is around 10, like we discussed before, and you can decrease the pKa value and make phenol more acidic, or increase the pKa value or make phenol less acidic by introducing different electron donating or electron withdrawing group in the ring, okay? But the phenol that we talked about earlier is right here, the simplest of the phenol. Like you said, you can see here, right? The highest pKa value for the phenol derivative right here is around 10.9. But if you look at alcohol, the lowest pKa that an alcohol has is around 15.5. Right, that's for the methanol. The one example that we took earlier was ethanol, and it's around 15.5, 16, right? Still much less acidic than the phenol and phenolic derivatives. Okay, it's just a graphical representation of the relative pKa values. So the next difference that I want to highlight is in terms of chemical reactivity. What's the reactive center for phenols? Right here, shown right here, versus the alcohol, tertiary alcohol shown here. Where does the chemical reaction happen? Which bond is likely to break in alcohol and phenol? Is it similar? Are they, when they participate in a reaction, does the bond break at the similar point? Okay, let's see. So what we're going to compare mainly in terms of is nucleophilic substitution reaction, which means whether this OH group would leave as OH minus or not. That's what we're going to compare. Okay, so in phenol, let's start with phenol. If the nucleophilic substitution reaction was to happen at this carbon center, let's say a nucleophile would approach and attack this carbon center, the OH group has to leave as OH minus, right? That's a nucleophilic substitution reaction. An incoming nucleophile will substitute a leaving nucleophile. But if the OH minus leaves here, then you are going to form a phenyl cation. This is the phenyl cation, a positive charge at this carbon center. And I'm going to tell you right here, the phenyl cation is not stable. And I'll tell you why. This is not stable. This is not going to form. And that is because you see this orbital structure right here. So this is the benzene ring, planar. These are the p orbital that represent the delocalized electron in the ring, right? So see the gray p orbital right here? This is the empty orbital that is formed as a result of OH minus leaving. And you can see by the symmetry here, that empty p orbital, because it was sort of planar with the ring, right? This OH bond is planar to the ring. This empty p orbital is actually perpendicular to the rest of the p orbitals in the benzene ring. And what that implies is these pi electrons can't be used to make this positive charge more stable. This can't be donated into this empty orbital because they are not lining up well. For a p orbital to donate, for a filled p orbital to donate to an empty p orbital, they have to stand parallel. So that's not happening here. So this positive charge or the empty p orbital is not been stabilized by these pi electrons in the benzene ring. As a result, the phenyl carbocation is not stable. As a result, this is not going to form, which means the phenol is not going to participate in nucleophilic substitution reaction at the carbon center. This OH minus group is not going to leave, which also means this carbon-oxygen bond is not going to break. Okay, keep that in mind. Now let's look at alcohol. Will this OH minus group leave? Well, first we know OH minus is not a good leaving group. So what we can do is we can introduce alcohol in an acidic medium, and we can protonate the OH. If you protonate the OH, then you are going to get then the OH is going to get converted into H2O, which is a decent leaving group. So once the H2O leaves, you are going to form this alkyl carbocation. And this alkyl carbocation with a positive charge on this carbon center is pretty stable because this has been stabilized by the inductive effect from this carbon and also the hyperconjugation effect from the CH bonds surrounding this carbon center. I've talked about hyperconjugation and inductive effect in my previous recordings, so you can always go back and refer to that. But unlike phenyl or phenyl carbocation, the alkyl carbocation is more stable because the CH bonds surrounding the cation will contribute towards the stability via hyperconjugation, and also the alkyl groups will contribute to the stability via the positive inductive effect. So the carbocation is likely to form. Okay, as a result, a nucleophilic substitution reaction will happen. Okay, whether it's through SN1, SN2 depends on the category of alcohol. I've already talked about SN1 and SN2 before, but the important point to keep in mind here is alcohol would undergo nucleophilic substitution reaction in an acidic medium. The OH minus can be made to leave, right? And the carbon-oxygen bond is able to break. That happens in case of alcohol. But in phenol, whether it's in acidic, basic, or whatever medium, the OH minus is not going to leave. The carbon-oxygen bond is not going to break. As a result, phenol is not going to undergo a nucleophilic substitution reaction. Keep that in mind. And also keep in mind this orbital structure and why phenyl carbocation is not stable. Okay, so basically nucleophilic substitution reaction is possible in alcohols but not in phenols. Okay, so two differences that we have learned about. The first, phenol was more acidic than alcohol, or phenol is more acidic than alcohol because of the relative stability, higher relative stability of phenoxide ion versus alkoxide. And the second difference is alcohol undergoes nucleophilic substitution reaction, the OH group can leave, the carbon-oxygen bond can break, whereas in phenol, the nucleophilic substitution reaction does not happen, the OH group is not able to leave, the carbon-oxygen bond is not going to break. And that's because of the poor stability of the phenol or phenyl carbocation, okay? Just keep these two differences in mind. Okay, so coming back to the summary, basically we talked about two important differences. The first difference was phenol is more acidic than alcohol, and that's because of the relatively higher stability of phenoxide ion compared to the alkoxide ion. Remember why phenoxide ion was more stable? The resonance structure, the delocalization of the negative charge on the oxygen atom throughout the ring, which is a good thing, right? And the second we talked about was the chemical reaction, where does phenol undergo a nucleophilic substitution reaction at the carbon center? It does not, right? But the alcohols do. And that's because of the poor stability of the phenyl carbocation and relatively higher stability of the alkyl carbocation in case of alcohol. Just remember these two differences. Okay, so yeah, thank you very much for listening, and I'll talk to you guys soon. Take care. Bye.